So, just briefly, what are the institutes and colleagues contribute to this study? This is a numerical model for pollen prediction, and the test was done with the thunderstorm asthma case in Australia. Why Australia, you will see a bit later. But these are three institutes: Institute of Physics collaborated in this research, participated, Republic Hydromet Service of Serbia, and University of Technologies in Sydney, Australia. So the major objective of our experiments study was to develop a kind of new approach for pollen prediction, modeling, and just let me say a few words about the process of pollinization and pollen transport. In our case, this was a grass fields in Australia as a major source, but of course there are a number of other pollen types. They are different in size, in terms of particles, pollinization seasons, and so on. Again, we are focusing for one particular case with extreme health consequences. When pollen enters to the season, the key parameters which cause the emission is the near surface wind, but also some other atmospheric parameters like temperature, humidity, and so on. So you can see in this scheme, in this picture, what is the major concern and our target of the research in this study. Pollen starts with emission from the surface, and if there are thunderstorm conditions coinciding with the season, in that case there is a large possibility that whole pollen grains enter to the cloud, exposed to high relative humidities, strong winds, even electric forces, and after that there is hypothesis that pollen grains rupture or opens and release a number of small close to micron particles, so-called subpollen particles. So this is the process that has been studied for almost 2 decades, but the problem is that the current models, most of the current pollen models doesn't include these subpollen particle effects. The other thing that I would like to mention, that these small particles that are released after the whole grain are ruptured are very tiny particles, close to 1 micron, and they easily enter to the lungs and cause so-called thunderstorm asthma. This is the terminology introduced by Australian colleagues. So what was our approach? We just used one of the aerosol models that we developed over 20 years. Basically, we started with the dust emission and transport, but the process of aerosol is common for any aerosol type. And we just rearranged this DREAM, Dust Regional Atmospheric Model, to work for pollen. And what was our intention to add not only, to have not only whole grain pollen particles, but also to include SPPs. So DREAM poll is, for the first time in the community, a model that predicts formation and dispersion of SPPs, which are released after intact pollen, whole pollen grains burst in a thunderstorm convective environment. So on the right, you can see the general scheme, how any of aerosol enters to the atmosphere. There is a emission at this first stage, vertical motions, horizontal transport on a longer range, and finally wet and dry deposition. So in our case, prognostic, one of the new prognostic equation is pollen concentration, whole grains. And in addition to that, as I said, we also added as a prognostic parameter SPPs. The model itself is designed anyway for forecasting purposes. It predicts pollen or any other aerosol 2 or 3 days in advance. And on the bottom, you can see a sketch how the process of rupturing happens. So you have here the whole grain with number of tiny particles inside. Then under atmospheric influence, these small particles are released. About 700 to 1,000, these small particles are coming out from one pollen grain. And then this is the start of the new life of these small particles, and the model takes into account this process. This is somehow a repetition of the previous talk or description. We start with the intact pollen. The pollen is transported in the vertical. If there is some unstable atmospheric conditions, these particles enter to the cloud, are broken, and after that they are released and they are transported down to the surface. And if on their way there is a populated area, you might expect some health response. So as I said before, current pollen models in the community, most, not all of them actually, predict only intact pollen, but not SPPs. So this is the major information that we have to keep in mind. Intact pollen, which are from 20 to 70 microns in diameter, are necessary but not sufficient condition for asthma occurrence. So basically these large particles are stopped at the area of nose or eyes, but they really cannot cause the asthma response. So the model that should include SPPs basically would permit or stop frequent false alarms that occur in our current pollen prediction models. So this is why we started to deal with this aspect. We selected Melbourne 21st November 2016 catastrophic thunderstorm asthma episode. Why catastrophic? Because in this particular case, this was the largest ever globally case when nine deaths happened. Ours, 4%. So once again, why Melbourne 21st November 2016 is selected as a case? Because on that afternoon, there was a coincidence of a high concentration of pollen coming from the grasslands. That's one thing, but also coinciding with a very strong thunderstorm conditions in the atmosphere. And as a result, at the end of this day, 9 deaths happened. Then within 30 hours, about 1,000 percentage of increase was in asthma-related hospital admissions compared with 3 years behind. So it was extremely emergent situation for the city, but also very strong pressure to the health authorities. And this was the largest ever worldwide thunderstorm asthma case, and that's obvious why we selected this to test the model, our model. So I have to mention that Melbourne is anyway one of the places mostly exposed to grass pollen with relatively frequent asthma case, thunderstorm asthma cases. Of course, it happened from time to time. 3 times in 2010, as you can see in the table, are identified cases with thunderstorm asthma, and the largest one in 2016. So that's very delicate to develop a system that is sufficiently accurate not to produce frequent false alarms. These are rare events, but when happen, they really make a lot of problems to the community. So a few slides just illustrating how the model works. So on the left top, you can see the field, the similarities field of the surface concentration. And Melbourne is this red point always. So this system was transferring together with the thunderstorm, and once it accessed the Melbourne area, we could see also in the simulation how it looks in the cross sections. Once again, here is Melbourne. There is some topography here, and one can notice that there is upwind motion in the front of the unstable squall line, and behind downward flow, exactly like as you can see in the conceptual thunderstorm models. And the last slide here is the cross-section for the SPP concentrations. And this was the moment when the whole system just passed the the Melbourne city. Another set of graphs, outputs of our model, shows the following. The green, yellow to green part are intact concentrations. This is time, by the way, and this is height. So soon after that, about 2 or 3 hours later, it was the structure colored in blue, and these are the concentrations of SPP. And this is typical situation that first come the intact pollens into some particular place when there is a thunderstorm, and soon after that there are more lighter but more dangerous also SPP concentrations afterwards. And concerning the verification of our results, this was most tricky part, because for whole grain particles, we have relatively good measurement networks everywhere, I would say, today on the West, in Australia as well. But for SPPs, there is no operational methodology that could, for example, measure every hour or so the concentration. So you can do all of this work, but in the laboratory afterwards. Anyway, the green curve here is the simulated concentration of whole grains, and it is comparable with the observations that we had for this particular case. But for SPPs, you can see here the maximum few hours later, and this point indicates when hospital admissions started in Melbourne. So it correlated well with the moment when our model predicted 1 day in advance possibility of difficult health conditions. So in conclusion, we have several open questions in our study. One of them is, should the model generate frequent false alarms? So we ran the model just only for 2 days around 21st of November. If we extend this for the whole month of this year, maybe also over the 2010, which was also very much. Melbourne was exposed to frequent health conditions. What should be the result? So, shall we also produce frequent false alarms? We don't know for the moment. In any case, actually, I would say that we know a bit more about that, but the article that is going to describe these conditions for two extreme seasons is in preparation, and I hope that we will soon submit the article. The other plan of our group is to perform experiments with different pollen types, like ambrosia or birch or some other, just to test the capability of the model to play with not only with one type of pollen grains. And the other, the behavior of the model for different geographies. For us in Europe, that's more important to have a forecasting system covering central, let's say, Europe, Balkans, and some other. And this is our next thing or next plan to transfer the model for other geographical domain. And of course, the final goal of our work is really to develop operational daily forecasts with a model with added SPPs, those small and tiny particles that really cause the asthma epidemics, not only the whole grains, and again to test if this model works and produce at least minimum of false alarms. Thank you.
Thank you, Slobodan. And we are over time, so
yes,
I don't know if you have any questions, but 4 excellent talks, so I felt that we should give you all the time to
that's fine.
some information, very different topics and very timely topics from SARS to...
Excuse me, one question from...
There's a question,
here,
please.
Yes.
I was just wondering, how are they detected, these FPPs?
Sorry, how?
How are they analyzed? How are they detected?
There is a recent article of American group. They analyze in the laboratory, and as far as I understand, this is kind of a fluorescent method. I'm not in measurement domain. Yeah.
No, thank you.
But once again, there is no operational, nowhere there is operational measurements of SPPs.
All right, thank you. And I think if there are no questions for Slobodan or any other speaker, I don't think.
Excuse me, it is one more question.
Okay.
From participants that are not able to ask by the voice. It is from Slobodan's colleague Tihomir Popovic. He asked how are the initial values of pollen grains per unit area determined by which the modeling was started? Is there real-time pollen monitoring in this area?
For this area, as far as I know, the Australian local government is trying to establish a physically based model just from 2017. As far as I know, they're still trying to develop a useful modeling tool for that. The recently published reference from this group announced that they are still not close to the situation that they can predict these SPPs. I mean, to predict the whole grains is not a big deal really today. But this group is still not with some conclusive, how to say, work about that. Talking about the experiment we used in the study are the real-time masks or distribution of sources for this particular year and this particular month.